Today I'll be presenting my deep enforcement learning project on the banana navigation environment. This project implements a deep queue network agent that learns to collect yellow bananas while avoiding blue ones in a 3D environment. In the banana environment, the agent navigates a 3D world with the goal of collecting yellow bananas for a +1 reward while avoiding blue bananas that give a -1 penalty. The state space consists of 37 dimensions, including the agent's velocity and ray-based perception of objects around it. The agent can take 4 discrete actions: moving forward, moving backwards, turning left, or turning right. The environment is considered solved when the agent achieves an average score of 13 over 100 consecutive episodes. To solve this problem, I implemented a deep queue network, or DQN. The neural network architecture consists of an input layer with 37 neurons corresponding to the state space, 2 hidden layers with 64 neurons, each using ReLU activation functions, an output layer with 4 neurons corresponding to the possible actions. The key components that make DQN effective are an experience replay buffer that stores past experiences and allows the agent to learn from them multiple times, a target network that stabilizes the learning process by providing consistent Q value targets. The DNQ algorithm works by predicting Q values, which represent the expected future rewards for taking a specific action in a specific state. During training, we compute Q value targets using the Bellman equation, the intermediate reward plus the discounted maximum Q value of the next state. These targets serve as the correct answers that our Q network learns to predict. A key innovation in DQN is the use of a separate target network that updates less frequently, which stabilizes these targets and prevents the feedback loop that would otherwise make training unstable. Well, in simpler terms, this means that the Q value targets tell the agent, this is how good we now think the action is. And the action updates its neural network to better predict these values. We will look at this more in the next slide. An epsilon greedy policy that balances exploration of new actions with exploitation of known good actions. The DQN learning process works as follows. Number 1, the agent interacts with the environment, taking actions and observing the resulting reward in new states. Number 2, these experiences are stored in the replay buffer. Number 3, periodically a mini batch of experiences is randomly selected from that buffer. Next, the target Q values are computed using the reward plus the discounted maximum Q value of the next state. Number 5, the Q network is updated to minimize the difference between its predictions and these target values. And finally, the target network is occasionally updated to match the Q network. A crucial aspect of reinforced learning is the balance between exploration and exploitation. Exploration involves trying new actions to discover better strategies. This helps the agent discover optimal paths and prevent it from getting stuck in a local optima. It's especially important early in training. Exploitation involves using known successful actions to maximize rewards. As the agent learns which action leads to high rewards, it can exploit this knowledge. This becomes more important later in training. The epsilon greedy strategy manages the trade-off by choosing random actions with probability epsilon and the best known actions otherwise. To gradually shift from exploration to exploitation, we implement epsilon decay. At the start of training, epsilon is set to 1, meaning the agent explores 100% of the time by taking random actions. As training progresses, epsilon decreases according to a decay rate of 0.995 until it reaches a minimum value of 0.01. This means by the end of training, the agent is exploiting its learning knowledge 99% of the time, while still occasionally exploring to potentially find better strategies. This chart shows how epsilon decreases over the course of training episodes. For this project, I used the following hyperparameters: a learning rate of 0.0005 for the atom optimizer, a discount factor of 0.99 to balance immediate and future rewards, a replay buffer of size 1000 experiences, a batch size of 64 for training updates, network updates every 4 steps. With these parameters, the agent successfully solved the environment in 469 episodes, achieving an average score of 13.4 over 100 consecutive episodes. And this is showing my agent gameplay. you can see that the agent is collecting yellow bananas. And whenever we get to an area that has a blue banana, it will change course. So here are the main talking points for my training results. So first, let's look at the moving average. This graph shows the moving average score over 100 episodes. As you can see, the agent started with very low performance, averaging only about 1 point per episode, or around episode 100. The learning curve shows steady improvement through episodes 100 to 400, with the agent crossing the solving threshold of 13 points around episode 500. After that, we see the performance stabilizing around 12 to 13 points, indicating that the agent has successfully learned a robust policy for collecting yellow bananas while avoiding blue bananas. The second graph shows the raw score for individual episodes. Notice the significant variability in performance from episode to episode. This is normal in reinforced learning due to the exploration process and the stochastic nature of the environment. Early episodes have consistently low scores, but as training progresses, we can see higher peaks performance appearing. By episode 400 to 600, the agent regularly achieves scores of 12, 15 to 20 in many episodes, with some exceptional runs exceeding 20. The high variance in later episodes demonstrates that while the agent has learned a good policy, there's still room for further stabilization and improvement. Comparing both graphs highlights the importance of using a moving average to assess agent performance. While individual episode scores can fluctuate dramatically, the moving score provides a clearer picture of the overall learning trends. The smooth curve of the moving average confirms that our agent is consistently improving over time rather than just having lucky episodes. The training results show that DQN implementation successfully solved the environment in approximately 500 episodes. This demonstrates the effectiveness of deep reinforced learning in mastering complex environments with continuous state space. The agent learned to extract meaningful patterns from the 37-dimensional state space and develop a strategy that maximized awards. While the basic DQN algorithm successfully solved the environment, there are several improvements that could be enhanced through performance. Double DQN addresses the overestimation bias in Q learning by using the online network to select actions and the target network to evaluate them. This leads to a more accurate Q value estimate. Prioritize experience replay also improves sample efficiency by prioritizing experiences with high temporal difference errors, focusing learning on the most informative transitions. And dueling DQN separates the estimation of state value and action values, which is particularly beneficial in states with some actions don't affect the outcome. Previously, we have done a program where we used Taxi version 3 environment. So it's instructive to compare the banana environment to the simpler environment of this Taxi v3. The key differences are the Taxi environment has a discrete step space with only 500 states, while the banana has a continuous state space with 37 dimensions. Taxi can be solved using tabular Q learning, but banana requires function approximation using neural networks. Taxi is a simple 2D grid world, whereas banana is a complex 3D environment, and neural networks in DQN allow for generalization between similar states, which isn't possible with the tabular method. These differences highlight how DQN extends reinforced learning to more complex and realistic problems. So in conclusion, this project successfully applied deep reinforced learning to solve banana navigation environment. The key components of experience replay, target network, and epsilon greedy exploration were essential to stabilize and optimize the learning process. There are several promising extensions to the basic DQN network that could further improve performance and learning efficiency. Most importantly, the techniques demonstrated in this project form the foundation for solving more complex sequential decision-making problems in areas such as robotics, autonomous systems, and game AI. Thank you for your attention, and thank you for taking the time to explore this project with me.